So we have problem number 7. Consider the Lagrangian L equals 1/2 m q dot squared minus 1/2 m omega squared q squared plus gamma q dot. Part A, compute the canonical momentum. Part B, construct the Hamiltonian. Part C, show whether gamma q dot term changes the physical motion. And part D, find a canonical transformation that removes the gamma-dependent term from the momentum. So this is canonical formalism problem. So for part A, canonical momentum, assume m, omega, and gamma are constants, and L of q comma q dot equals 1/2 m q dot squared minus 1/2 m omega squared q squared plus gamma q dot. And the momentum conjugate to q is going to be p equals partial derivative of L with respect to q dot. So p is going to equal mq dot plus gamma q. And if we go ahead there and solve for the velocity, we're going to get the following. Q dot here equals p minus gamma q divided by m. So that's part A. Moving to part B, construct the Hamiltonian. So the Hamiltonian is defined by the Legendre transform. H of QP equals PQ dot minus L. And first, PQ dot equals quantity MQ dot plus gamma Q times Q dot equals MQ dot squared plus gamma Q dot. So we get H equals M Q dot squared plus gamma Q dot minus the quantity 1/2 m Q dot squared minus 1/2 m omega squared Q squared plus gamma Q dot, close parentheses. And that's also going to be equal to the following: 1/2 m Q dot squared plus 1/2 m omega squared Q squared. So using Q dot equals P minus gamma Q over M, H of Q comma P, so H Q comma P equals quantity P minus gamma Q squared over 2M plus 1/2 M omega squared Q squared. And if we go ahead and we expand that, H Q comma P equals P squared over 2M minus gamma over M PQ plus 1/2. I don't know about the focus here, if it's in focus or not. So this 1/2, there we go, quantity M omega squared plus gamma squared over M times Q squared. Okay, so from there, since P and Q are classical variables, their order does not matter here, and what we could do from there is we could check using Hamilton's equations. So building on that, checking using Hamilton's equations, the first Hamilton equation is going to give us Q dot equals partial derivative of H with respect to P, and that's going to equal P minus gamma Q over M, which agrees with the momentum relation. And the second is going to give P dot equals negative partial of H with respect to Q equals negative gamma over M times the quantity P minus gamma Q minus M omega squared Q. And over here, because MQ dot plus gamma Q and P dot equals M Q double dot plus gamma Q dot. And the Hamilton equation, and that's going to become the following, and then we have M Q double dot plus gamma Q dot equals Y Q dot minus M omega squared Q. And so Q double dot plus omega squared Q, that's going to equal 0. Okay. So from there, that's after performing the computation. And moving along to letter C. Letter C here, does the term gamma Q dot change the physical motion? Okay, so what we could do here is we could observe that gamma q dot equals d dt gamma over 2 q squared. So L equals L naught plus df dt, where L naught equals 1/2 m q dot squared minus 1/2 m omega squared q squared. So f of q equals gamma over 2 q squared. And adding a total time derivative to a Lagrangian, that does not alter the Euler-Lagrange equation when the endpoint positions are fixed. And this can also be checked explicitly here. So we have partial derivative of L with respect to q dot equals mq dot plus gamma q. So d dt partial derivative of L with respect to q dot equals m q double dot plus y q dot. Now also here a partial derivative of L with respect to q, that equals negative m omega squared q plus gamma q dot. And the Euler-Lagrange equation is mq double dot minus gamma q dot minus the quantity negative m omega squared q plus gamma q dot, close parentheses there, equals 0, which simplifies to mq double dot plus m omega squared q equals 0. Okay, so from here, adding on to part C. So here, so we could say for q double dot plus omega squared equals 0, consequently, the gamma q dot term does not change the physical trajectory. It changes the canonical momentum by the shift p equals m q dot plus gamma q, but not the equation of motion. The general motion is going to remain q of t equals a cosine omega t plus b sine of omega t. And moving along into part D, the canonical transformation, removing the gamma-dependent momentum term. What we want to do is introduce new canonical variables by q, capital Q equals lowercase q, p equals lowercase p. So capital P equals lowercase p minus gamma lowercase q. So then capital P equals m q dot. So capital P is the usual mechanical momentum. And verification that the transformation is canonical, we use these using the Poisson bracket here, this QP, Q, and then comma P minus gamma Q, QP, and then minus gamma QQ, that equals 1. And then also this QQ bracket here equals 0, and the PP equals 0 respectively. So we could say the transformation here is canonical. And a type 2 generating function that provides it is f sub 2 of q comma p equals q capital P plus gamma over 2 q squared. So p equals this partial derivative of f sub 2 with respect to q equals p plus gamma q, and p equals p minus gamma q. And from here, q equals here this partial derivative of f sub 2 with respect to p, and that equals q. Okay, for that type 2 derivative, type 2 generating function with respect to q, with respect to capital P equals lowercase q. So because f sub 2 has no explicit time dependence, k equals h plus partial derivative of f sub 2 with respect to t, and that sorry about that, equals h. And substituting lowercase q equals capital Q and lowercase p equals capital P plus gamma capital Q into the original Hamiltonian, we get k of this q comma p equals bracket capital P plus gamma capital Q minus gamma capital Q and close bracket squared divided by 2m plus 1/2 m omega squared capital Q squared. So k of q capital K k of capital Q comma p equals p squared over 2m plus 1/2 m omega squared capital Q squared. And this is the standard simple harmonic oscillator Hamiltonian. Okay, so that's all for problem number 7. Thank you very much and have a great day.